For today, and probably for the next class as well, we're going to talk about sequencing in SuperCollider. And sequencing is really important because music and sound art, they are inherently bound to the concept of time. It's a time-based art. And so far we've been making synth defs and playing tones and this and that. And the way we move through time is to manually kind of step through the code and evaluate this line, evaluate that line. It's pretty limiting in that sense. It's very nice to be able to specify through code some predetermined or partially determined, somewhat random musical sequence. Maybe a sequence of synths that are created, or maybe a sequence of numbers which are used to feed into some synth process. If we unpack the world of music and programming, almost everything is some sort of sequence. It's a really valuable set of tools to have available. I don't think I'm going to assign homework today for a couple of reasons. One, I think this is going to be a 2-class lecture, so let the concept sort of sink in. I'll give you homework a week from today. And also because next week, a week from today, is going to be the take-home midterm exam. So I also want to give you some time to review what we've covered and just prepare for that. And also to give you some information on the format of the midterm. It'll be a 24-hour take-home midterm. What I'm going to do is look back over the homework assignments that have been graded and select 3 or 4 problems, no more than 1 per homework assignment, and tweak the problem in some moderate way. So it's similar but different. So it'll be 3 or 4 problems based on previous homework problems taken from various homework assignments. And you'll just go home and you'll have 24 hours to complete it and submit it. And it's open notes. Everything's available. Just no collaborating with others, basically. All right. Well, to start off this lecture, I have prepared some code ahead of time. Just what we're looking at right here. We boot the server, and this is a slightly more sophisticated version of the code that automatically reads subfolders of audio files into buffers. I've gone one step further here. We're using some of the same concepts we've seen before. We have this process.now executing path, which returns a path to this file. I create an empty event. It's an unordered collection structure where each item has a name associated with it called B. I create a path, which is the string to the parent path. And I have, let me find the materials here. So here's the folder in which this code file exists. Right here, the one without the word notes. And then I have a subfolder called audio, which contains 3 subfolders, each of which contains some additional audio files. So we have these flute sounds, these glitch sounds, and these wood sounds. So let's just walk through what this code does. We have a variable called subfolders, which represents the entries or the items within the audio folder. And so those are the 3 subfolders: flute, glitch, wood. So subfolders is an array of path names representing the path to those 3 subfolders. We then iterate over that array of 3 subfolders. So we do this function once for flute, once for glitch, and once for wood. We pass in the path name representing the subfolder. We declare a variable called buff array. And then we iterate within the iteration. So we iterate over the items in each subfolder. So on the first pass, subfolders.do, this is the flute subfolder. And we say, OK, what's in that flute subfolder, and iterate over those. Pass in each item, which is a file, happens to be an audio file. And we read that file into a buffer. I'm using read channel and just reading the left channel. Some of these are stereo, some of these are mono. So I'm just making it uniform and making them all monophonic buffers. And then we store, we create a symbol name in the event B, which is the name of the subfolder converted to a symbol. So in the first case, this is going to be the symbol flute. In the next case, the symbol glitch. And then finally symbol wood. And each one of those symbols points to this array of buffers. I imagine this might take a little bit of time to digest fully. I just wanted to walk through it here, but essentially we run this code, and then what we have is an event in B, which has the following keys: flute, glitch, and wood. So we can say B at flute. This is an array. So there's an array stored in the event B at the name flute. And this array has size 9, because there are 9 samples here. So we can say B at flute at 0. Sure enough, that's a buffer, so we can play it. Then we have all the other 8. It's a flute tongue ram. It's an extended technique where you sort of ram the tongue against the sound hole of the flute. We also have these glitch samples. Just pick one and play it. And also the wood. It's actually different samples, but it's the same piece of wood, so they're all very, very similar. So anyway, this is a nice, compact piece of code which we can freely add subfolders. We can add files to subfolders, and this code will work every time. It'll simply go through, take each one of those subfolders, grab its contents, iterate over the contents, and load each one into a buffer, and it stores them very nicely in this event structure, where each item in the event is an array of buffers in that subfolder. Then we have a synthdiff, and this is stuff we have seen before. We have a play buff. We can specify the buffer, the rate, the start position, and whether it will loop. By default, it does not loop. I'm passing the signal through a low-pass and high-pass filter in series, and the cutoff frequencies are such that the filters have essentially no effect on the spectrum, but we can high-pass or low-pass when we create a synth if we wanted to. We have an envelope. This is my usual go-to envelope where we just have 3 segments. It's kind of a slightly curved trapezoidal shape. Apply the envelope, pan, apply an amplitude, and send it out. So just to demo some of these, what we can do here. Here's our flute samples. We can filter. We can change the rate. Etc. Stuff we've all seen before. I've set all this code up so that we have stuff to work with and we can save a little bit of time as we get into sequencing. So the first object, the first new class I'd like to introduce is routine. And a routine is basically a special type of function, a function being just a code enclosed in curly braces. A routine is a special type of function which can be evaluated incrementally. So you can evaluate part of a routine, and then a routine remembers where it is, and you can tell it to resume where it left off. And when you execute a routine, it can be stepped through manually by calling next, and you get the next bunch of code until it's told to wait again. Or you can play a routine, in which case the routine is scheduled on a clock object, and you can basically specify time intervals to wait between certain code evaluations. So let's look at a very simple routine. And what we'll do is take this synth and put it in here 3 times, and we'll say 6, 8, 11. And we'll just take the zeroth buffer within the flute subfolder. All right, so this is basically roughly the same as a function, which does the same thing. Here's a function. Let's put it in parentheses here. And if we evaluate this function, what happens is we get all 3 of these, but basically at the same time. When we evaluate code in SuperCollider, a function or elsewhere, the code expressions are parsed and interpreted and executed sequentially. But what computers do is they do things as fast as they possibly can. So realistically, these 3 statements, when we evaluate the function, are separated by a microsecond or so. But they're so close that we can't even perceive a difference. It sounds simultaneous to us. If we make a routine and either call next on it or call play, we get the same thing. Right now, we have this routine, but we have not instructed it with regard to where we'd like it to wait or pause or something like that. So the simplest way to segment a routine into discrete evaluations is to put wait times. We use a number and we say dot wait. I guess we can also put one here. So when we create this routine and play it, this value, if we do nothing else here, if we don't customize in any way, what happens is when we play a routine, it gets scheduled on the default tempo clock, which exists whenever we launch SuperCollider and is permanent and always counting beats. And it has a default tempo of 60 beats per minute, or 1 beat per second. So technically, these are being interpreted as beats. But with our current setup, 1 beat equals 1 second. So there's not much of a distinction to be made. If we try this again, it doesn't work. It doesn't work because the routine has reached the end. So we can reevaluate it to basically refresh it or overwrite this global variable with a new identical instance of that routine, and then it will work. We don't necessarily need to reevaluate the routine. We can just call reset on it, and then we can do it again. So if we reset and then say next, what happens is, in this case, the routine will begin evaluating, and as soon as it encounters a wait, it stops and returns control to the main thread. So we've sort of moved through the routine. It executes this line of code. It encounters one.wait and says, OK, I'm just going to hang out here. You let me know when you're ready. And so we can say, OK, give me the next one. Whatever we like. And then we've reached the end. So next begins to return nils instead of the numbers associated with the weights. And again, we can reset at any time. It would be, like, imagine we wanted to make like a sort of a 60-note sequence or something. It'd be pretty obnoxious to have to write out, if we find ourselves doing this kind of thing, synth, wait, it's pretty tedious. It gets really clumsy because, if we want to change something, it's not a very good notation system. If we want to find the 37th note, we have to count manually, basically. There's just all sorts of problems with this approach. So we could make this a little bit simpler if we know our sequence like this. Right? We see there's a lot of repetitive code happening here. Right? It's almost the same line. So what we'll do is we'll say 6, 8, 11 dot do arg note, And then we can just kind of simplify it like this. And play it. This is a lot simpler because now we can just kind of add things here as we like. Let's make it a little faster. All right. Very simple routine. There is no need for sequences of sounds to be finite. There's nothing wrong with an infinite sequence so long as we have wait times tucked away in there. For example, if this was 0.wait, or if we just didn't have it, of course we'd just get all three of these basically simultaneously. Right? Because it just fires through that routine and does not wait at all. It just goes straight to the next thing. So we can let's make this a random number like this, and we'll just say 3.do. And now we're going to do this function 3 times. We don't need the argument anymore because we're just using do as a counter, basically. Do this once, do this twice. Picks a random number, and can't do it again. We have to reset it. It's kind of annoying. But we can say inf.do. Do this forever. And then it'll just play. We can stop the routine whenever we like. Once a routine is stopped, it's considered sort of a hard stop. So we can't really pause and resume a routine if we use the play method. We can't really pause it. Other mechanisms can be paused. Routine's a little bit simple, I guess, in this regard, but we can always reset, play, stop, reset, play. We can even daisy chain these two methods together. Probably the most important thing is to never do this. If you have an infinite routine, then you have an infinite number of steps. So if there are no wait times between the steps, you will immediately lock up your computer's processor because it will be, you're giving it an infinite amount of work and you're not giving it any time to breathe between that. So on Mac OS, you'll probably see the rainbow swirly. You'll start to notice that code does not return anything. Nothing appears in the post window. You'll try to click on one of these menus and it doesn't appear because the computer says, well, hold on, I've got a lot to do here, so you're going to have to wait. Yeah. So it's really, really important. When you are playing a routine and there's an infinite loop, of course, this is harmless. Well, no, actually, no. It's even if you say next on this routine, if you make this routine and then call next, it's just going to same problem because there's no wait. There's no place for it to stop. So wait times inside of infinite length routines. That is your number one thing to keep in mind, probably. All right, so routines they're pretty good for simple sequences like this, where you can just line up a few synths and play them. Let's do one more example before we move on to the next thing. You can nest iterations. So if we say, 6, 8, 11, 4, and we'll just say that note. So this routine will just play 4 notes, but you can say 4.do. Right? And close the whole thing in a structure like this. So you can define composite sequences pretty easily just by nesting iteration blocks inside of each other. And we could even do something like this. maybe not the most concise or elegant way to express musical sequences, but it is one option. And I find routines to be really handy, especially when you're dealing with large-scale things that have already been defined as a modular unit, where you can have a routine which says, do this function, wait for this much time, do this function, wait for this much time. And the functions themselves are actually quite complex and might spawn subroutines or something like that. So they do have their uses, and I'm introducing them here because they will come back into play as we start to talk about the more sophisticated tools in SuperCollider for creating sequential patterns. Okay, so routines don't necessarily have to make synths. They can also generate numbers, any kind of values. So let's imagine we want to generate a sequence of transposition values, like we were doing here. Instead of manually creating the array and iterating over them, let's make a routine called Notegen. All right, and we can specify our notes here. Let's see, it's the, yeah, and we're just going to say arg n dot wait. Seems a little weird because we're treating these as note numbers, but we're calling wait on them, but we're going to be calling next on this routine. So it's not, yeah, and so we've got this routine. Now if we were to play it, it wouldn't do anything. It would just, well, actually, I don't know what waiting for a negative amount of time means. It's not really, it doesn't make sense, but we're not going to play it. We're going to say Notegen dot next. And what happens is, as a side effect of, when we play a routine and we call wait, this value is interpreted as a number of beats to wait before rescheduling the next event. But when we call next, the routine simply returns the wait value. It spits it back out of the routine. So this expression on the first evaluation produces the number -7. So if we were to say, x equals, x would be now equal to -7. And now it's going to be -2 and -0. And just, so here, sure enough, x is equal to 0. So this is basically a little sequence generator that just spits out numbers. And it gets to the end and says nil. I guess we could wrap this in inf.do just so we never run out of numbers. It just keeps going over and over. Sometimes we even want several numbers at a time, so we can get the next 4 numbers. And it's just going through the sequences. Okay, here's an array of the next numbers. You can bundle them together. And again, you can reset anytime you like, and it starts back at the beginning. All right, so we don't have sound yet, but we have a routine which cranks out these numbers. So we can take a simpler routine, like maybe this one, and inf.do. Here we just simply put notegen.next.midi ratio. And just for fun, we'll pick a random wait time, either an eighth of a beat or a quarter of a beat. And let's not forget that we have all these synth arguments, right, that are at our disposal. Like the start position, we can subtly vary the playback rate a little bit more. We can change the envelope characteristics. We can pan it. Let's just do a slightly more interesting version of this. Copy this, bring it down here. So we'll multiply this by, oh, I don't know, a random value between something like that. We'll say the start position is going to be random between 0 and 2000. This is a frame value, so a number of samples to start into the file. Let's do this. So we might filter the sound a little bit. We might not. And we'll say no sustain, but the release will be random between something like, these are pretty short files anyway. I might even make them even shorter. See what this sounds like. Let's see. Oh, we got this is wrong. I did not mean to do a negative sign there. It was actually it was taking the playback ratio and then scaling it by some value between negative 0.97. So it was actually a huge range. Some of the values are probably close to 0. Some of them made it go backwards. Not what I was intending. I just wanted a small variation close to 1. Divide this by 2. Bring it down an octave. It sounds a lot stupider than I thought it was going to sound. The point here is that we have lots of arguments, and we can work them into the routine however we like. All right. So this more or less takes us to a class of objects called patterns. In the help browser, there is a category called streams, patterns, events. And this houses pretty much all of the classes related to this lecture and the one after it. So there's a routine is actually a type of object. It's a subclass of a class called stream. If we look up routine, you can see that 2 classes above it is something called stream. And a stream is basically a process that responds to next and play in the way that routine responds to next and play. Routine is a slightly more specific version of this, but routines and streams are largely the same thing. An event, we're not going to talk about events today, I don't think. Actually, we kind of already dealt with events. This here is an event, right? Our buffers are actually stored in an event. So an event is at its simplest just an unordered collection, but it has a specific sub-functionality within the context of streams and patterns. And then patterns are, it's a large family of classes categorized here. For example, we'll look in the list category, and most of them, I think all of them, start with a capital P. It's a clue that we're dealing with a pattern object. So with things like pseek, pseer, pseries, pshuff, prand. I think a nice way to describe what a pattern is it's basically a pre-packaged routine, or actually technically it's a blueprint or a recipe for a pre-packaged routine with a particular flavor, right? It picks a random number within a range. It goes through a specified sequence of numbers. It takes an array of numbers, randomly orders them, and then goes through that order. A million different flavors here. They're probably one of the biggest challenges of being introduced to patterns is learning which ones do what and being able to find the most relevant pattern when you have an algorithmic sequential idea. So let me start. For example, this routine here, this Notegen, where we have a specific sequence and simply spit out the values again and again and again forever, this can be expressed much more concisely using patterns. This is kind of the whole point of patterns. We don't have to build these custom routines ourselves. There's already a pattern that exists that allows us to do this. So the pattern that makes the most sense in this case is pseek, which is a pattern which defines a sequential output of values in an array. And it takes 2 arguments, an array of values and a number of repeats. And so there we have a pseek called p. And then we can say Notegen equals p.asStream. This is a key step here. And it underlies a much larger and more important distinction between the concept of a pattern and a stream. And to summarize that distinction, a pattern is a recipe or a blueprint for some tangible sequence, but it is not the sequence itself. It's just a set of instructions for creating such a sequence. A stream or a routine represents the tangible execution or actualization of that pattern. It's the real thing. It's the actual values that we can extract with next. So if we have this code here, we can say notegen.next, and out come these numbers one at a time. And we've specified inf, so as soon as it gets to the end, it goes back to the beginning. If we call next on p, we just get a pseq, pseq, pseq. Pseq doesn't actually know how to give its values. It only knows how to specify what they should be for when that pattern is used to generate a stream. It doesn't work. This is what we want. If we had replaced inf with a number, let's say 2, then Notegen would return this sequence of, what is it, 9 values? 8, 9, and then restart. Yeah. And gives that value, that sequence of 9 values twice, and then begins returning nil because it says, I'm at the end, I've got nothing for you. All right, let's look at a few other patterns just to give you a sense. I'll try to cover some of what I think are the most commonly used patterns for cranking out numbers. P rand, for instance, I'll just call this seq, right? Our actual sequence. P rand selects an item from the array at random and does so a certain number of times, in this case, an infinite number of times. So it just picks a random value. It could be any random value. Sometimes it picks the same one twice in a row. Sometimes it doesn't. It's just fully random. P xrand, almost the same thing, but it will never select the same item twice in a row. So we'll never see 2 10s, 2 6s, 2 3s. Now, if you do something like this, well then, it's not capable of distinguishing whether the items in the array are identical or not. So in this case, we might see 2 3s, one after the other. And so pxrand isn't super fancy. So it considers this 3 and that 3 and that 3 different things. But as long as all of the items in the array are unique, then it will never pick the same one twice. pwrand. The W stands for weight, not W-A-I-T, but W-E-I-G-H-T, which allows us to weight the choices using a second array. And this second array should contain the same number of items as this one, and the numbers should sum to a value of 1. So we can say 0.1, 0.1, 0.1, 0.7. And this means 70% of the time we're going to get a 10, and 30% of the time we're going to get one of the other numbers. So if we just do this, we'll see that it kind of favors 10s. Next n is what we want. A lot of 10s, mostly 10s. I personally find it kind of, like when I have a lot of numbers and I want some fairly specific weighting, I find it really annoying to have to manually make sure these numbers add up to 1. So another thing you can do is just kind of give some loose, loose weights that kind of represent, like just, doesn't forget about what they add up to. Here we see like, here's the biggest number, so that's going to dominate, and this one is the smallest, so we're going to get 3s not so often. And all we have to do here is normalize sum. This is a method which takes an array of numbers and scales them uniformly so that their sum equals a value of 1. So here we have the same proportional relationships between these numbers, but they sum to 1. So this lets us be a little bit more free in how we express the weighted choices. So same idea, lots of 10s, very few 3s. Make sense? Yeah. All right. These are all, let's just do one more, P shuff. Let's do 1, 2, 3, 4, 5, 6. P shuff takes an array, randomizes the order, and then sequentially outputs that order over and over again. Three, four, five, two, six, one. 3, 4, 5, 2, 6, 1. 3, 4, 5, 2, 6, 1. Sometimes what I don't like about prand is that it's totally random, and sometimes I actually want each item in the list to be generated at least once before moving on, but I don't always want the same order. And there's a little trick you can do with pshuff, which also introduces the idea of nesting patterns inside of each other. So we can, I think what we have to do here is pseek. I think this will work. Do that once, but do that forever. Let me just see if this works. 4, 6, 3, 2, 1, 5. 5, 6, 4, 1, 2, 3. 6, 3, 5, 2, 1, 4. What we've done here is we have, ultimately this is a pseek. And the item, the array it's sequencing through only contains one thing, a pshuff. And so when a pattern encounters another pattern in its process of generating values, it will embed all of the values of that pattern before moving on to the next item. So pseek encounters this pshuff and says, okay, I'm going to embed this pshuff, which says pick a random order of these 6 things and do it once. So it goes through and does that, and then it gets to the end and says, okay, that's the end. So back to the beginning, sequence this again, it encounters the pshuff again, picks a new random order, and again and again and again. If we had this backwards and did something like this, then this is no different from just doing the pshuff, because the pseek says do this thing once, do this infinite thing once. So this is going to give us the same random sequence every time. But if we do the inner pshuff once but make the outer pseek infinite, then we get a different random order each time. On the topic of nesting patterns, it's also very important to bear in mind that patterns that generate numbers, like these here, can be added, multiplied, divided together as if they were numbers. And what happens is that each pair of output numbers, that operation is applied. I'll give you an example. Let's say we want pan positions that are random between -1 and +1, like fully random in the stereo space, but we want each pair, each consecutive value, each adjacent value to have the opposite sign as the one before it. So there's a randomness, but the values are also alternating left, right, left, right, left, right. Now there's no one pattern that will do this, at least as far as I know. You can make a pattern that alternates between -1 and +1. I just use pseek and say -1, +1, inf. You can also use p-white. P-white, the white is a reference to white noise, and white noise is just a random value for every sample. So this is just going to give us values that are fully random between the float -1 and the float +1. So they're just random. These two are positive. This one is quite close to -1. This one relatively close. So they're just kind of fully random. But we can say, instead of this, if we want to do this alternating random pan thing, we make these values between 0 and 1 and multiply this by pseek, -1, +1. Right? So P is actually a special type of internally created pattern called a P binary operator. It's a pattern which is the result of applying a binary operator, like multiplication, to 2 individual patterns. Then we turn it into a stream so we can call next. And what happens is the first value is random between 0 and 1, multiplied by -1. The next value is a random value between 0 and 1 multiplied by positive 1. And then this random value by negative 1, because both patterns are going through their values, and this operation is applied to each corresponding pair. So we get negative, positive, negative, positive. Right? All the ones on the left here are negative. All the ones on the right here are positive. So we can use this stream called seek to feed into some synth process, and if these synths are being generated, then we'll just get this nice kind of random alternating left-right thing. Right, so that's p white. There's also p exp rand. So the equivalent here, this is like r rand. It's just a uniform distribution between min and max. This one here is like exprand, where it's an exponential distribution between min and max. And just like exprand, we're not allowed to cross or include 0 because the algorithm mathematically fails in that case. Here, for example, we get a bunch of values, and they are going to tend closer to the minimum because that's how an exponential distribution works. In fact, we can, here's a cool trick. We can plot them to see the difference. So here is p white dot plot. So we're just plotting those values. You can hit M to change the way the plot looks. A little histogram. And this, you can see the values kind of average around 0.5. That's what we expect. Here is p exprand. So it looks a little different, right? Values are kind of, there's a few outliers, but for the most part, they kind of tend towards the bottom. I should also add that if, just like r rand, if the min and max are integers, the results, that's not very clear. Let's just not plot it. How about that? The results are integers. But if either one or both are floats, the results are floats. P exprand always floats. But because this pattern outputs numbers, we can use operations, not just addition, subtraction, multiplication, but also methods that are valid for numbers. So we can round the output of p exprand to the nearest integer if we want. Other patterns. Let's see, a couple more I can think of. P series. P series is an arithmetic series with a starting point, a step amount, and then a number of values to generate. So this is going to start at 1 and add 4 each time. You can go the other way, obviously, subtract 4 every time. I think this is particularly nice for decibels. If you want to go down by 1 decibel each time, and you just want to sort of make something, just very, very easy way to make a, instead of having to, like pseq would be, you could do pseq here, but it's really ugly, right? It's just a lot of, you can use it kind of a shortcut, like pseq, let's see, 0, -1, -99. This highlighted code here is a shortcut for that array. So you could do this. Don't need that. This has the same result, but so there's more than one solution in almost every case. In fact, this trick right here of getting a random value to alternate left and right, I can think of at least 2 other slightly different solutions, different ways of combining patterns to produce the same result. Maybe that'll be a homework problem or something. But the key is to think about these patterns as if they're just numbers, right? A sequence of numbers, and you can apply any operation that would be valid for a corresponding pair of numbers, or even just to one pattern, any operation that would be valid there. The related pattern to P series is P geom, which is a geometric series, so it's multiplicative instead of additive. So, for example, powers of 2. So the number is multiplied by 2 each time. We start at 1, we multiply by 2, multiply that by 2, multiply that by 2. And this tends to be pretty good for amplitude. So this is great, just reducing the amplitude by half each time. It's a nice way to create a nice sort of fade out. You use a geometric pattern and apply that to the amplitude, and then things just get quieter and quieter and quieter. The place to look for these is you go to the browse, streams, patterns, events, patterns, and then you can sort of pick a category here. So random is going to include PX brand, P white, a few others. Some of these are there's really quite a number of patterns, and most of them are exotic and ones that I've never found the need to use. The ones that I'm using here are, I don't know, maybe it's just me, but I tend to think in terms of music as like, well, you can do things deterministically, so p-seq or whatever, or you can do things randomly. Pick a range, pick something from an array. You can sort of explore on your own. List also includes some interesting patterns here. But I feel like I've covered a lot of what I consider the essential value patterns. All right, so I wanted to give you just a quick teaser of what we're going to talk about next week. These patterns are all classified as and considered value patterns. They specify a sequence of values, usually numbers. Not necessarily. There are some exceptions, like for example, p-seq can be used to spit out. Let's copy this real quick. Anything, doesn't have to be numbers. P-seq, we'll say, for example, names of synth-defs. So the first one is the symbol sign, then the symbol saw. Right? So p-seq, you can put anything in a p-seq. It's just going to output that thing, next, next, next. P-rand is the same way. You can put anything you like in here. But things like p-white, these have to be numbers. It does not make sense to pick something between sign and saw. Right? It has to be numbers. So anyway, these are all value patterns, for the most part, all value patterns. And there is a pattern called p-bind, which is sort of the backbone of the pattern library, one of the most commonly used patterns. And it is a pattern which does not generate a stream of values. It generates a stream of events, the actual class called event. And you might think, what's the use in that? And the use is that within the structure of an event, there is an architecture, a bunch of code that exists in SuperCollider, which defines a complex hierarchy of actions to be taken when an event receives the play message. And it's so complex and sophisticated that even the empty event plays a sound. And so you might think, wait a minute, we didn't even make a synth-def here. Like, where is this all coming from? And it's all deep under the hood. So we can say things like freak 500. Right? We can say amp 0.3. So all sorts of little secrets tucked away here. We can even say instrument and use the synth-def that we've created earlier, and then feed in some things like buff, the at flute at 0, amp 0.8. Right. So what happens here is when we play an event, there's a large tree of branching decisions, and it figures out which type of event to play. The default type is the note event, which uses the synth-def based on the instrument key, and then feeds any additional information into arguments specified as additional keys. So pbind is a pattern which which specifies the generation of a sequence of these events and uses value patterns to determine the algorithms by which values are plugged in to these keys. So pbind is called pbind because it binds values to keys. So that we have an event with key value, key value, key value, key value, and then when you play a pbind, each individual event gets played. And so it's a way of automating very elegantly these kinds of structures. Instead of having to write them all out, we specify a value pattern for buff. We specify a value pattern for rate. We specify a value pattern that determines how many beats to wait between successive events. And then we play it, and all of this happens automatically. It's very nice, very beautiful. It's one of the most powerful features of SuperCollider, which we'll get into next time. But for now, I just wanted to introduce the idea of routines and then patterns, value patterns as little prepackaged routines as a very easy way of getting an algorithmic sequence of values. Right. Very good. So we'll continue here where we left off 1 week from today, and I'll also assign the midterm 1 week from today as well. So stick around if you have questions.